I don't know why I quit animating. Yeah. All right, so we're ready to go. So today we're going to start looking at how the symmetry in the molecule connects to the character table. So those rows in the character table are called Mulliken notation or different, what they're called irreducible representations. Think about the word representation. So each one of those rows represents a different symmetry in the molecule. Only the top row is the fully symmetric symmetry. So if something looks completely symmetric in all directions, it's top row. A sphere would be top row, okay? Any motion that goes in all directions at the same time would be top row. So think about like benzene, all the hydrogens stretching out and all the hydrogens coming in, that would be top row because that's fully symmetric. But how did we get here? Well, we started with the Lewis dot structure. We used the valence shell electron pair repulsion theory to move everything around in 3D to get a 3D shape. And then we looked at that geometry and we ran through the point group flow chart and came up with a point group. Okay, now that we know the point group, we can pick the character table in the list of tables that you have. And then we have access to the rows. So those rows will describe everything the molecule can do, okay, including the electron cloud. So this is the character table. We have to get this character table because of the point group. So that Schoenflies notation, and C2V, D2H, D2D, all those different character or point group representations, point group notations would be how we choose the character table. If we get the geometry wrong, we get the point group wrong. If we get the point group wrong, we have the wrong character table and everything is all falling apart. Okay, so it's very, very important. Then we get to this side piece. Each of these rows are we call Mulliken notations or irreducible representations. So that will really only make sense if you knew about a reducible representation. But you can take all of the motions in the molecule and you can produce a representation that represents all of the motions. And then you break those down into their irreducible representations. And so this is, we're not doing that exercise. That's something you probably will do in advanced inorganic, or certainly if you go into graduate school, you'll run into the reducible and irreducible representations. In this class, we're just dealing with that problem already finished. We just have the rows of the character table. And the word irreducible just means that they're not combinations of any of the other rows. It's another way of saying they're orthogonal too. So like our wave functions needed to be orthogonal, these rows are all orthogonal to each other. So it's just a little side trip on what that means by irreducible. Then over here in the middle, we have the characters, which we talked about. You operate on the wave function and you have some number out front that tells you what happened to that wave function, whether it was flipped over or what have you. And then we have these Cartesian and rotational basis functions. Okay. Let's see if I can do this. Let's think about water. Okay, so we've got water. My head is the oxygen. My hands are the hydrogens. Where's the z-axis? Up and down. That's the C2 axis. So we put the C2 axis along the z. And so x, y. So y is over here. So if I take y and look at the first column, the E column, the E column is just multiplying everything by 1. If I multiply the y-axis by 1, does it change? No. So I have a plus 1 right here. Okay. What happens if I take that y-axis, we're just showing you the positive values on y, and I rotate them by a C2? They're now inverted, aren't they? See the minus 1? Okay. What if I take the y-axis and I reflect it in the xz plane? It's now over here, minus 1, okay? What if I take the y-axis and I reflect it in the zy plane? No change, plus 1. So you can see those ones and plus ones and minus ones represent, their representation, they represent the symmetry of what happens to all these different things. We have other kinds of things like rotation around x and rotation around y and rotation around z and those kinds of things. So there's lots of different things that the molecule can do that are captured over here in shorthand, and that work has already been done for you. Like, you don't have to go through what happens to the y-axis and look at the characters, when you just find y on here, you come across and know that y is B2. And y'all have already done that to some degree in getting ready for that test and in the lab. So we'll do more of that today. So then the top row is the only row with symmetry. So if there's an integral over all space that contains the top row, so it can be A1 plus a bunch of other stuff, as long as there's an A1 in there, then the integral is non-zero. If there's any other odd symmetries, these integrals are all zero. So this is how we get to our selection rules using symmetry. And that's why that front meme where I'm sitting there saying group theory is easier than calculus, this is what I'm talking about. So here are all the molecular motions in water. So put a star on this page in your notes because of this thing here, this degrees of freedom. So if I have an atom in space, now my whole body is an atom, I can only do three things. I can move in the x direction or back, I can move in the y direction, and I can move in the z direction. So every atom has 3 degrees of freedom. What if I have 2 atoms? Each atom still has 3 degrees of freedom. They can all move in the x, they can all move in the y together, they can all move in the z, so that's translation. Okay? They could, if they tried to move in opposite directions, the molecule doesn't move, but they're vibrating. And it can rotate around each other. If this one tries to go in this direction and this one goes in that direction, because if they want to stay connected, they're going to have to rotate. So every atom has 3 degrees of freedom, even if you put it in a molecule. But some of those degrees of freedom are restricted if you want to keep the molecule intact, and they become vibrations or they become rotations. But there's still total 3 times the number of atoms, degrees of freedom. That makes sense. I want that to sink in. Total degrees of freedom for a molecule, you count up the number of atoms and multiply by 3. That's the total number of degrees of freedom. What do I mean by that? It means, how do I describe the motions and the positions of those atoms? I need 3 numbers for every atom in the whole molecule. So just think about x, y, and z coordinates. If I'm going to build that molecule and I'm going to write out the coordinates for every atom in that molecule, every atom has to have an x, a y, and a z. You add all those up, it's 3 numbers for every atom in the molecule. So for water, we have 3 atoms, times 3 should be 9 degrees of freedom. So we end up with 9 total motions in the molecule, 9 things it can do. So 3 of those are always translations. If the whole molecule moves together in one direction, that's called translation. So I'm not vibrating, I'm not rotating, but I am moving in space. So even though my body is made up of a gazillion atoms, I still only have 3 translations. So there's always and only 3 translations, because you have the whole thing moving in X, the whole thing moving in Y, and the whole thing moving in Z. That's it. Okay, that makes sense, right? You just have 3-dimensional space. So if I want to move through space, I only have 3 options, X, Y, or Z. Now, of course, you could do combinations, but the point is you could break that combination in. If I went diagonal, there'd be a portion in X and a portion in Y. So then you have rotations. For a nonlinear molecule, we can rotate around the Z-axis. So if I'm this molecule, I'm rotating around Z, okay? And then I could rotate around X, which would be like a cartwheel. Okay, there's a YouTube video of me doing a cartwheel, but I've stopped doing that. Jennifer made me. She's like, we can't afford the insurance payments. So, and then I could do a forward roll, which is hard on my back on the ground, but I could do that. I could rotate around this axis, okay, or back flip. I used to. I was in gymnastics, even if you could believe that. So those are the only 3 rotations, X, Y, and Z. Now, I make a point about a nonlinear molecule, because of a linear molecule, if there's no we know something's rotating because of its moment of inertia. And if there's nothing off the axis, there's no moment of inertia. And so there's no rotation around Z for a linear molecule. It's just not defined. Okay. The moment of inertia for that rotation is in the denominator, and it blows up if you're dividing by 0. So even mathematically, you can't calculate it. So that rotation disappears, and it shows up in the vibrations. Okay, but you can rotate around this direction and this direction if you're a linear molecule. So you have 2 rotations for a linear molecule. So y'all want to write that down. 2 rotations for a linear molecule and 3 rotations for a nonlinear molecule. 2 rotations for a linear molecule and 3 rotations for a nonlinear molecule. I put this on just about every test from this point forward, so these are easy points to get. And I'm always shocked. I get to the final after 3 tests and I ask how many degrees of freedom for vibration for a molecule and people can't calculate it. And I'm like, man, I tried. so that's why I'm emphasizing this so much. Okay. And then the vibrations are everything that's left over. So it's 3n minus 6 in this case. What's the minus 6? Yeah, the rotations and the translations, because those are not vibrations. So by definition, if anything moves the center of mass of the molecule, it's not a vibration. Okay, and if it's a rotation, it's not a vibration. All the bond lengths and angles are the same. It's a rigid molecule, it's just spinning around, so it's not vibrating. So anything not a translation or not a rotation is a vibration of the molecule. So we sort of define the vibrations by difference. So what's the 3n? That's the total degrees of freedom, minus the translations and the rotations. So you're basically, we're saying mathematically, everything else is a vibration. So we have, in this molecule, we have very easy way to add it up. We have 2 bond lengths and an angle. And so there's our vibrations, 2 bond lengths and an angle. Now, if you were to, in the old days, like when the scientists were trying to figure out these modes of vibration, they actually put like heavy spheres, you know, iron or whatever they made them out of, together, and springs, and they had like suspended them from the ceiling so that they would be, you know, bouncy, and they could pull on a OH and let it vibrate, and you could never vibrate one of these OHs without vibrating the other one, because they're 2 springs connected to a center mass, and so they act in concert with each other. But you can still count them that way. If you have 2 OH bonds, you're going to have 2 OH stretches. And if you have 1 angle, you're going to have 1 bend. So it's very easy to count up the number of types of vibrations. Benzene, complicated molecule. I've got 6 carbons, I've got 6 hydrogens, so 6 CH bonds. I know I'm going to have 6 CH stretches. Now they're going to be crazy combinations with each other, but I still know that I'm going to have total of 6 CH stretches, because that's mathematically what I've got. Okay. And so I've got 2 OH bonds here. I'm going to have 2 OH stretches. And how would they go together? Well, they can stretch together, and that's the symmetric stretch. So you see both these with the arrows, they're both stretching at the same time. And then here's the asymmetric stretch. One's compressing while the other one is stretching. So that's asymmetric. And that's it. I've got two of these now, and I've taken into account both of my OH stretches. And then this one in the middle is the symmetric bend, where you're just changing that angle between the bonds. So that's everything water can do with its vibrations. And this will be in the infrared part of the spectrum. Yeah. You can't do a rotation around the symmetry axis. Yeah, so there's nothing off axis to rotate. There's no mass off, so it can't be defined. And if it were rotating, you couldn't tell. You couldn't look at the masses and know anything was happening. So what happens is that missing rotation shows up in the vibrations. So let's write that down. For a linear molecule, it's 3n minus 5. So 3n minus 5, let me write that down too, so you know what I'm talking about. So right here, 3n minus 5 for a, oh gosh, I'm so upset. Okay, let's see if I can do this. Okay, not too bad. It's down here by these little PowerPoint tools. You see them pop up? When I get down, so it's so hard to write down there. Linear molecule. Okay, is everybody cool with that? Can you read my chicken scratch? So it's 3n minus 5 because we've lost one of the rotations. Okay, good. So these top ones are easy. They should always be easy. Once you've got the Cartesian coordinate system, you know the rotations. RZ is this one. You know, this is X, so RX is this one, and RY is this one, rotating around this way. So those are easy. The translations are super easy. I'm moving all in X, I'm moving all in Y, or I'm moving all in Z. So those are super easy, and they're easy to find on the character table because you'll see X, Y, Z, RX, RY, RZ. You go find the character table, you'll find their symmetries. Notice these symmetries are labeled. RX rotation is B2, RY rotation is B1, RZ rotation is A2. So you just find the row in the character table that has those designations and you know their symmetry. Down here, these, if you're not given this A1 here, it might be tricky to figure out. So we're going to do that today, figure out how these vibrations are assigned. So if we take the symmetric stretch, let's say we didn't know this. Like let's say we didn't have this piece on the screen. And let's say we didn't know this part right here. So we just knew it was the symmetric stretch. So we have the arrows here showing that both hydrogens are stretching at the same time, okay, in phase with each other. They won't stretch forever. There's a bond there, so they'll turn around and they'll come back. So they're going out and back, out and back. That's the symmetric stretch. Have y'all ever, it depends. You never can tell what they taught in high school math classes at every school, right? Some schools skip some things. Did y'all do component vectors? So this is a diagonal vector, but look at the Cartesian coordinate system. There's a Z component where it's moving down, and then there's a Y component where it's moving out. If you haven't covered that in high school, you've covered it now. All right. So this diagonal vector can be the sum of two vectors, one that's going down in Z and one that's going out in Y. Okay. Notice the Z components all have the heads of the arrow on the same end. The arrow's heads are on the bottom. But look at the Y components. The Y's are opposing each other, so they cancel out. Can you see that? Okay. So the Y components cancel each other, and only the Z components are left. So what that means is the hydrogens, which are positive, are getting further down in Z, and the oxygen's moving up just a little bit to keep the center of mass from moving. And so we're getting a longer dipole moment. The negative end is getting more negative, the positive end is getting more positive with distance. And so this dipole moment is oscillating. And we just need to compare it to the Cartesian system that we've drawn. It's oscillating along the Z-axis. So we would designate this motion as Z, having Z symmetry. So we would see that motion aligns with the Z-axis, so we call that Z symmetry. Then we go over to the character table and we find Z in that top row, and then we go over to the left and we see it's A1, and so now we know that it's A1. So you start with the arrow picture, you figure out what's happening with the motion, and you try to find where the dipole moment is oscillating. So it's oscillating along the Z-axis. So you would say this has Z symmetry. Go to the character table, find the row, it's A1, A1 symmetry. Why do we care? Well, because we want to know if the selection rules are allowed or forbidden. So we're going to put this motion into a transition dipole moment integral and just use the symmetries to tell if it's zero or non-zero. So we have to turn this motion into one of the rows of the character table. Okay, let's do another. Here is a picture of it. So this is not water, but it's a very similar molecule. It's a C2V molecule. And you see the symmetric stretch of the formaldehyde CH stretches. So every C2V molecule will have some kind of motion like this. Let's do this symmetric bend. So here again, compare the Z components. They're both going down, oxygen's going up, and the Y components are both coming in, but they're both pointing at each other and they'll cancel out. And so this is also a dipole moment that's getting bigger along the Z-axis and smaller when it stretches, or when it oscillates. So we would see those blue arrows that haven't canceled, they're all along the z-axis. You might say, but the oxygen up arrow cancels with the hydrogen down arrows. And they're on different atoms, and so they're not canceling because they're on different atoms. And they're what's creating the dipole moment. So the oxygen's moving up, which is negative, and the hydrogens are moving down, which is positive. And that's going to interact with light that's polarized on the z-axis. So light coming in the molecule polarized like this molecule doing this motion, it's going to interact with that oscillating electric field along the z-axis. So we find Z in the character table. It's on the top row. So this is an A1 motion. So this motion would be labeled with the symmetry A1. Okay, let's do the asymmetric stretch. So A means not, so not symmetric. The Z, now this hydrogen's going down, this one's going up, and so now the Z components cancel on those hydrogens. And the Y components don't cancel. So this one is going to the right, or to the left, sorry, this one's going to the left. So the Y direction is not being canceled, but the Z direction is. And so this dipole moment is oscillating left and right. And it's completely oscillating. It's going like it's zero in this direction, but when those hydrogens move, all of a sudden a dipole moment appears along the y-axis. And when the hydrogens move back through their equilibrium position, it goes to zero, and then it appears in the opposite direction. So even though this is a weak dipole moment, its change is huge. So it goes from zero to pointing in positive y, and then zero pointing in negative y. And that's going to really strongly interact with light. So the asymmetric stretch would be a strong absorbing transition. So we find y in the character table, and that's B2. Is everybody? Yes. They're on the same type of atom. Yeah. So the hydrogens are moving together. And so you look at the hydrogens and see which ones of those cancel, but you don't cancel them with the oxygen. Yeah. Yeah. And this is in terms of their, like, what kind of electrical effects they have, right? So, but for the motion of the whole molecule, they do all cancel because the molecule doesn't move, right? But in terms of their electrical effects, we're looking at what's happening to the hydrogens and whether the positive charge is getting stronger or negative or less strong, or going from positive to negative like it does in this case. And so here's the asymmetric stretch in formaldehyde. So you can see that if that's the positive charge is sloshing back and forth, left and right. Okay, and there's a negative center, but this side's becoming very positive, and then the other side's becoming very positive as those hydrogens are moving back and forth. So light that's oscillating like this would be able to interact with that motion if it matched the frequency, and that's where we get the transition. So light like this at this frequency would interact. Light like this would not interact. It's just a different location in the spectrum. It wouldn't have a peak there. So now let's talk about the selection rules. There's something interesting about vibrational levels. This is the first time we've seen the vibrational potential energy function, the parabolic curve. That's how energy grows in terms of the displacement of a spring, a ball on a spring, or a pendulum. You've seen that from classical physics. And we now have quantized energy levels in that potential energy surface. It's kind of like our particle in a box, but it's different in a few ways. In this case, the even numbered quantum states have top row symmetry. Also, the ground state is quantum number 0, not 1. In the particle in a box, the lowest state was 1. In this case, the quantum number is V. You see, here's the quantum number V. And then here they are right here. So V equals 0 is the ground state for vibration. And every even vibrational state is top row symmetry. So I say top row instead of saying A1 because in a molecule like benzene, it's A1G because it has an inversion center. But in our case here for like water, this doesn't have an inversion center, so there's no G's and U's. For something like CI, it's just AG. There's no one. It's AG and AU. So you have to look at the character table and the point group to know whether it's A1 or AG or A prime or A1G, etc. But still, the even quantum states and vibration are all top row symmetry. The odd number quantum states are the state function, are the symmetry of that motion. So like we had the Y one, that was B2. So every other one would be B2. So that's what we have for the asymmetric stretch. Look where the B2s are. So B2, 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 way up. Now, molecular orbital wave functions do not alternate in a regular pattern. I would say people really mess this up. So if you want, I mean, I put a star on this page too, because a lot of times the very first thing they learn that vibrational slide that I just had, and then they think they always alternate, but not in molecular orbitals. Molecular orbitals can be whatever the symmetry of that cloud looks like. Here's water's molecular orbitals. The ground state is A1. You see the symmetries are listed right here. But then this first excited state is also A1. You see it's not alternating. This one is B2. The next one is B1. Then we have B2 again, and then we have A1 at the top. So it's like you have to look at the cloud and figure out what kind of motion it is of the electron cloud and look at the character table, and then you can pick the symmetry. So let's practice that. So let me look here. Let's look at this one. This is our formaldehyde molecule. Now, when we draw the shading on molecular orbitals, well, first of all, let me see. Raise your hand if you've seen a molecular orbital before, like in organic chemistry. Raise it high so I can see. So everybody's seen molecular orbitals. So you've seen the shaded region and the non-shaded region. Or if we got a color screen like this, we have different colors for those molecular orbitals. Those colors represent the lobes in the wave function. Remember the slinky. When we were in that first excited state and it was doing this, if I were to freeze the frame, like right here, this side is decreasing while this side is increasing. It's on the path. So this side would be a certain color, and this side would be the opposite color. So that's what we have going on with molecular orbitals. It's just hard to show them in motion without animation. So this is an animation. You see the color switches, and red represents shrinking, and green represents expanding. So that's what's happening to the electron cloud. When you draw those colors, one of those is positive, means expanding. The other is negative, means shrinking. That positive and negative does not mean charge, because these are electron orbitals. They're all negative. Okay, so it's how that orbital wave function is changing in time. So does that really help? Now, every molecular orbital you'll see the motion of that electron cloud when you think of it. Now, compare this motion to the Cartesian coordinate system. Just look at it there. I've got the Cartesian coordinate system right on the center of mass of the molecule. Do you see that it's only changing along the z-axis? So it's moving up and down. That electron cloud is sloshing up and down. It's not really changing along y. A little bit, but it's in both directions on y. Okay? Just like our arrows would cancel if vibrating in opposite directions on y, those would cancel. Same thing with this electron cloud. What is the charge doing in this molecule? It's oscillating up and down. That's the charge oscillation. And that's going to interact with light along the z-axis, because light's an oscillating electric field. And you can see that in this molecule. If that's what the electron cloud's doing, and light comes in like this, then it could absorb light along that z-axis. If light's coming in like this, and it sees this oscillation, there's no interaction. It's 90 degrees to it, okay? So we see this motion, we assign it z. So what about this one? On the count of three, say your axis that you think it goes. 1, 2, 3. Do it again. 1, 2, 3. Yes, I love hearing the right answer. Okay, so it's sliding left and right. And if light comes in like this with an electric field and my electrons are doing this, they can interact with each other. If light comes in like this and my electrons are doing this, they don't even see each other. So now for some practice. Let's do ammonia. Okay. So what about this top one? So that's the electron cloud being shown all red. So what's it doing? It's expanding in all directions and shrinking in all directions. Expanding in all directions, shrinking in all directions. What did I say at the very beginning? I said if it's expanding in all directions, it's top row. Top row. So that one's fully symmetric. There's no nodes. So that would be top row. So that one would be A1. Okay. And then down here, I guess it would help if I drew the coordinate system. We're looking right down the C3 axis. So coming out of the plane of the paper would be the Z axis. And so then this would be X, and this is Y. Oh my gosh, what is that? Okay, Y. So this one is sloshing left and right. You see that? And that's along the x-axis. So this one has X symmetry. And this one is sloshing up and down. So with our coordinate system, that's the y-axis, so that's Y symmetry. So we would go to the character table and find that X row and the Y row, and in a threefold or higher molecule, they're on the same row. So we get E symmetry. It's doubly degenerate. So what we're saying is that the energy of the X motion and the energy of the Y motion have the same energy. So in this molecule, anything with threefold or higher symmetry is what we call a symmetric top. And that means the X and Y have the same moment of inertia, okay, and the same energy. Whether it be the electrons moving in X and Y or the molecule vibrating in X and Y, they're going to have the same energy and the same symmetry. Okay. So let's go back to this thing that I skipped over, this flow chart. So this is a flow chart. That's kind of hard to see probably, but what we're doing is we're taking a picture of let's use this one. So we're looking at the molecule up there, and we're asking this question. You see the molecule, you see the electron cloud with its colors, and you see the X, Y, and Z coordinate system right next to it. And so the first question, is the positive X the same as the negative X in terms of the color change? So I'm coming out and I see that one side's red, the other side's green. I go back and the one side's red, the other side's green. I haven't seen any change as I walk along the X-axis. Okay. So I would say, is it the same as? Yes. So it'd be X squared would be one of the possible rows for this motion. Okay. Then I go to the next question. Is the positive Y the same as the negative Y? So if I walk in positive, I go into the red zone. Or no, green. I go into the green zone. Okay. If I walk in negative Y, I go into the red zone. Totally different. So I would say no to that question. And so Y would be a possibility for this motion. Okay. And we just showed that if it's oscillating in Y. So we know the answer. Okay. But and then the Z, is the Z the same as minus Z? I'm standing on the origin, I look up, I see red and green, on opposite sides. I look down, they're still on the same side. And so there's no change in Z. So a possibility would be Z squared, after looking at that motion. Why squared? Well, think about it. If you square the Z axis, all the numbers are the same. Okay, so I looked up and they were the same as when I looked down. If I were to square the axis, they'd be the same looking up and the same looking down. So that's a way to sort of make both ends of the axis look the same, is to square them. So that's the square piece. Okay, so then we look at that sort of x, y, and z, we analyze its behavior, and then we come over here and it says, is there a single x, y, or z symmetry? Yes, we had this one. There was a single y symmetry. So we go over here and say, choose the x, y, or z row in the character table. So we just analyzed it. Does it change color when I go to Z, or does it change color when I go to Y or X? It did change color when I went in Y, so it's the Y row. So I just took what we did before and kind of made it into a little flow chart. Sometimes it will change along two of them. And so then we end up with X times Y, or X times Z, or Y times Z. And so that's when this flow chart really becomes useful. There's a combination of X, Y, or Z. If everything is squared, then it's going to be top row. It's going to be the X squared, Y squared, Z squared row. Okay. We did this, we did this. Okay, so let's look at our examples.